Newton's first law of motion, sometimes called the law of inertia. Before we introduce Newton's laws of motion, we want to make sure to understand a couple of concepts. These are mass and force. You may have heard of mass being defined as the amount of matter in an object. Another way to define mass is to say that it is the measure of an object's inertia. Inertia is defined as how resistant an object is to changing its velocity. Imagine that you have two objects sitting at rest. The one on the right contains more matter or has a greater mass. Your past experience probably tells you that the more massive object weighs more. Now imagine trying to push each of them to slide them across the floor. Moving them across the floor would mean changing their velocity from zero velocity to a non-zero velocity. Which one would resist this change in velocity more? Your past experience probably tells you that the one that weighs more or has a greater mass would. This is correct. The object with the greater mass has a greater inertia or is more resistant to a change in its velocity. The mass is a measure of this inertia, meaning it gives us a way to assign a value to it that can then be compared with the values for other objects. Mass is measured in the SI units of kilograms, and mass is a scalar quantity since it only has a magnitude, and direction would add no meaning to it. A force is an influence that causes an object to change its velocity. When you slid this object across the floor, you applied a force to it in order to change its velocity. This pushing force is considered a contact force, where you made contact with the object. There are also non-contact forces, also called action at a distance forces, that cause objects to change velocities, such as the force of gravity. The unit for force is an SI unit called a newton, and force is a vector quantity because a force has a magnitude and a direction. This brings us to Newton's first law of motion, which states that an object continues in a state of rest or in a state of motion at a constant velocity unless compelled to change that state by a net force. If our object is sitting on the ground in a state of rest, it will stay in that state of rest unless a net force is applied to it. And if it's moving at a constant velocity, it will stay doing that until a net force is applied to it. This net force could increase the object's positive velocity, or it could decrease the object's positive velocity. What is a net force? The net force is the vector sum of all the forces acting on an object. In reality, our object on the floor has other forces applied to it, such as a frictional force from the floor. Let's look at another example of my car on the road. What forces are acting on it? It's on the earth, so the force of gravity is acting on it in a downward direction. Newton's first law suggests that a net force will cause a change in the velocity of my car, so why doesn't my car move downward through the earth? The gravitational force on my car must not be the net vertical force. There must be another force acting upward on my car. We'll call this the force from the road. In order for my car to continue to have zero change in its vertical velocity, these forces must cancel each other out, giving us zero net force in the vertical direction. A zero net force results in no change in the velocity. A zero net force could mean that no forces are acting on an object, or, as in this case, it could mean that forces are balanced, canceling each other out and adding to zero. What if my car is moving to the right at a constant velocity? There's a force from the engine that moves it to the right, but if it's continuing to move at a constant velocity, then the force from the engine can't be equal to the net force. Otherwise, its velocity would be changing according to Newton's first law. So, to balance it out, there's a frictional force from the road that acts in the opposite direction as the force from the engine. In order for the car's velocity to increase, for it to accelerate, the force from the engine will need to be greater than the frictional force from the road. In that case, we would have a non-zero net force to the right, and the car's velocity would change. Note that when we consider vertical motion, we look at the vertical net force, and when we consider horizontal motion, we look at the horizontal net force.